meeting. He's going to be here for a long time, though, because he's going to be our Secretary-Treasurer for the Cal SFS. But he's presently working for the Desert Research Laboratory, but soon will be a professor at CSU Monterey Bay. So let's get him started with his slideshow.
Thank you, Jim. Yeah, so I'm ending my 30 years in the wilderness. I originally came from California, but it's been a long time, and it's good to be back. So I've been interested in the conductivity, total dissolved solids, salinity in streams for quite some time. I originally started trying to develop models that predict electrical conductivity in streams, looking at the spatial differences among streams, primarily wanting to predict the natural background concentrations. So these models are already being used here in California to help or to help determine where reference sites are, and they're used other places for other things. This is an example of the model being applied to the entire United States, every stream in the US. You see these broad spatial differences in conductivity that occur. Here I'm showing you high conductivities in red and low conductivities in blue, and that's going to be the way I'm going to show conductivity the rest of this talk. So I've moved beyond spatial and looked at temporal differences among conductivity. I wanted to see how conductivity might change with given climate change. So basically I took my conductivity models, replaced all the current estimates of climate with future estimates of climate from climate change scenarios, and then basically developed predictions of conductivity, how much it's going to change across the United States over the next 100 years. But as somebody pointed out, it doesn't take a lot of courage to stand up and say what's going to happen long after you're dead. It's much more difficult to actually talk about what's going to happen in a shorter time frame. So recently I've been wanting to look at the effects of conductivity on drought on conductivity I should say, both in terms of the natural background, how will the natural background change, what we're going to see at reference sites, and where you have human uses already altering conductivity, how will that interact with drought to increase change, and how will this then affect biota in streams. So this is a project I've just recently started with the EPA and Tetra Tech. And we're kind of in the middle of it, so you're getting a snapshot here where we're at. We're making progress, but we're not quite done yet. The opportunity to do this comes from several different places. First off, we've got a very consistent way of measuring conductivity. We've been doing it the same way for about the last 30 or 40 years with hundreds of agencies across the United States going out and collecting hundreds of thousands of observations of conductivity. So we have this large data set of observations. We compare that now with both temporal and spatial climate data at relatively high temporal resolution, so monthly to weekly observations of evapotranspirations from MODIS satellites or PRISM climate estimates going back over a century at monthly intervals. And now we have watershed analysis tools that allow us to look at large amounts of data relatively efficiently. The watershed analysis tool I've been using lately is StreamCat, as talked about earlier by Jerry. What the StreamCat process does, it takes in landscape layers. Any sort of landscape layer, could be ecoregions or satellite data or anything in between. And it uses the NHD's already calculated subcatchments to basically calculate catchment averages. And the trick, what StreamCat does, is it basically allows you to accumulate these things in a downstream direction. So every single subcatchment going downstream basically accumulates everything that happens upstream. So you're actually getting watershed averages. And this exists both as data and as a process. Ryan Hill, who developed this at the EPA, has basically produced data sets for many of the things that Jerry already talked about that I've been using. And I basically applied this to climate data. So what StreamCat does, it basically gives you a summary of everything, all the watershed conditions for a given stream segment. So the stream segment is actually the level of spatial resolution I'm going to be operating at, not actually at points, but actually at stream segment scale. So we can take a look at a stream segment, basically look at all the observations that have been made along that segment by different agencies, and collect all these data and basically associate them to that stream segment, which then gives you all this environmental information. So I basically hoovered up all of the, actually Tetra Tech for me and myself, we went both together, we went out and basically took from STORET, from the USGS NWIS system and USDA, took all the available conductivity measurements that have been made. And it was roughly about 1 million conductivity measurements made over the period between 2000 and 2015. And we associated that with all the stream segments in the NHD and basically went through and basically sorted these out and screened them for land use, impervious surface, population density, permitted discharges, mining, and fertilizer use to basically pick out the least impaired sites out of this entire data set. But at the same time, trying to maintain some ability to have sites from across the United States. So this is a map showing you the roughly 2,000 sites that survived my screening process. So we basically withheld 5% of our data for validation. And at these a little over 1,800 sites, we had over 12,000 observations of conductivity over the 15 years. Gives you a mean number of observations of a little over 6 per site, with a range of, most sites had only a single observation, but some sites had up to 165 different monthly observations over the 15 years. And the histogram there at the bottom basically shows you what the distribution of observation is over time. You can see we have a relatively consistent set of observations over time. So with StreamCat data, we basically have the geochemical, geophysical, topography, vegetation, atmospheric deposition, and soils already calculated for us. The only thing I really need to go back through and do is the climate. So we basically ran 4 different climate variables through the StreamCat process. We looked at maximum temperature and mean temperature, both of which have been in my previous conductivity models, as well as evapotranspiration and precipitation. And essentially we basically calculated every single monthly average from over the entire 15-year period. So it was 192 months that we looked at for all 4 of those variables. And from these, we then calculated, for every observation, we associated that observation for that monthly climate, as well as the month prior to that, the month prior to that, the 3-month average, the previous 6-month average, and the previous 12-month average. I was happy to see plenty of random forest talks yesterday, so for those of you that attended all 3 talks about random forest yesterday, this is a repeat, but for those of you who weren't here, a real quick refresher on random forest. It's a modeling technique that uses a classification and regression trees, basically to build empirical models where you associate response to predictor variables. Each one of these trees is actually a separate model, but what random forest does is it basically bootstraps the data and creates thousands of trees from different random sets of data, and then makes predictions by averaging across each of all these models. And the advantage of random forest is it's very resistant to overfitting and effectively models nonlinear data as well as incorporating interactions. But one of the limitations is it cannot extrapolate. So this is my natural background model that I recently created, recently being Friday. Here I'm showing you the observed to predicted conductivities. And you can see we got a generally pretty good fit, the red line there being the one-to-one line. We're not really showing much evidence of bias, although there's a slight tendency perhaps to over-predict conductivity in a certain number of sites. But the R-squared was almost at 0.9, and the root mean squared error was only 73 microsiemens. When we take that 5% of sites that were validation sites and apply the model to them and look at their predictions, we basically see that the external validation is basically in agreement. We're having the same set of, R-squared close to 0.9, a slightly higher RMSE. And that's primarily due to this one site with multiple observations that was being over-predicted by the model for some reason. I'll have to go back and take a look and find out why we had that over-prediction for those sites. One of the things about random forest that lets you do is you can pull out the partial dependence plots that show you how each predictor performs in the model. So this is showing you how rock calcium oxide content in the watershed is related to conductivity if you're holding all other predictors constant. And you can see as rock calcium oxide content increases, conductivity increases. And you also can extract out the importance of each variable. What random forest will do is it'll basically remove the information of that variable and see how much the average error increases. So the greater the increase in error, the more important that predictor is to the model. So up in the upper right-hand corner there, I'm showing you the variable importance. So if you look at all the static predictors in the model, the first 2 most important variables were both geologic, rock calcium oxide and rock sulfur, which is consistent with my previous models. We expect geology to have a really dominant effect in terms of natural background. Soils showed up in 5 different variables with Well, like things like sand and soil permeability being negatively related to conductivity, and water table depth and soil erosion measured by K-factor having been positively correlated. And atmospheric calcium deposition, that's the one that's not highlighted there, was relatively important. Basically, that's a measurement of how much dust is being deposited. So when you have a really strongly granitic catchment with very little erosion occurring, dust can actually be an important source of ions to that stream. And percent conifer was the other static predictor. Looking at the dynamic predictors, the 12-month average maximum temperature was the most important of my dynamic predictors, but precipitation showed up in 3 different measurements. The 6-month average, the 3-month average, and the month prior were all important predictors in this model, as well as the 6-month average evapotranspiration. So I took one site by hand. I picked out the Sisquoc River near Sisquoc's gauge because it was measured essentially almost every month over my period of record that I was interested in. I basically withheld this as an external validation data site, but this was hand-picked, not randomly picked by most of my sites. And here I'm showing you my model's predictions there in blue over the 15 years, or correction, 10 years, the last 10 years of data, and the observed conductivity at that site. And this is a reasonable, for my model, I think this is a reasonable representation. We have a slight bias at this site. My models are slightly under-predicting conductivity. And as you can see, like especially during the height of the drought, we were seriously under-predicting. It didn't quite capture the drought effect. But we do have a general agreement and trend between the 2 data sets, between the observed and the expected here. Obviously, you can make a much better prediction if you use a SWAT model that was calibrated to this site. I'm not going to argue that these models will work as well as a SWAT model might work or other process-based models. But the advantage of this approach is over one of the process-based approaches is now I can go and talk about every other stream in the entire state. So this is a map showing you for October of 2015 what the conductivities were across the state. And now I can look at every single month and see how conductivity changes as the year progresses. And you can see where the largest changes are occurring. If you focus up what was happening in Northern California, you can see some really large changes in conductivity occur there. I'll run that through one more time. So here I'm showing you the water year 2015. As the water year progresses, you have lower conductivities early in the winter, but then once summer approaches, you see the conductivities are increasing, especially in Northern California and across the Sierra foothills. And now we can compare drought to non-drought years. So on the left here, I'm showing you the July 2005, which was a fairly wet year for California conductivities, and comparing that to July 2015. And just by looking side by side, the general patterns are the same, and certainly Southern California, it actually showed very little difference between the 2 years. But Northern California shows some dramatic differences. And actually, we subtract these values from each other, we can actually come up with a map showing you exactly how much conductivity changed between these. Here in red and black, I'm showing you conductivity increases of over 100 microsiemens. So you can see that the Sierra foothills and the Northern California coast showed dramatic increases in terms of conductivity between wet years and dry years. So this is still a work in progress. There's still more validation work that will need to be done for these models. One of my problems with my models is the fact that I really can't predict beyond 2,000 microsiemens, and there are sites that have naturally occurring high conductivity, so I need to come up with a high conductivity model, which this data will allow me to do. I'm going to go and take this natural background concentration data, calculate the alterations that's occurred with land use, and then basically come up with an alteration model that will allow me to look at the effects of human activities. And finally, we'll apply this to biological models. Tetra Tech Lei Zhang has developed some biological models he's already begun to apply. This is showing you the relationship between the natural background at a site, the increase in conductivity, on the y-axis, and with the red lines, what the general trends in taxa loss with invertebrates are. So if you have a site with a natural background of 100 microsiemens, such as we have in Northern California in many places, and you have 150 microsiemen increase in conductivities, like we saw with the 2015 drought, that would actually lead to a 10% loss of taxa, even in these reference sites. And with that, I'll stop and take any questions. Yeah, Dave.
Yeah, I was wondering if you've been able to
here.
take... Right. I was wondering if you've been able to take also changes in discharge across those streams and look at that relationship to shifting electrical conductivity over that same kind of a time frame with discharge.
So there are runoff estimates. The runoff estimates are not temporally specific, so it only gives you the spatial signal. So I actually have ignored those runoff estimates and relied only on precipitation, which is temporally dynamic. Now, with some of the models we talked about yesterday, if you actually have a temporally dynamic model, it would let you actually estimate runoff from precipitation, and that way we could actually do that. That might be interesting to do. Yeah, Rafi.
Could you talk a little bit about your strategy for developing a model for these sort of naturally high conductivity streams?
So my strategy is a work in progress. So one of the problems I've been struggling with, I was trying to develop a model that would do the high conductivity and low conductivity sites at the same time. But essentially, because there's so many low conductivity sites and such a few number of high conductivity sites, the signal gets swamped essentially, and you can't really effectively do that. I've already tried modeling just the high conductivity sites by themselves, and that doesn't work very well either. So I'm actually going to probably do a random selection of low conductivity sites and basically build a balanced data set between low conductivity and high conductivity sites and try to model that and see if that gives me a better model. I think it's lunchtime.
Okay, thanks.